Hi there. We're going to work on our electronic structure homework questions here, and so we're going to look at these questions and go over those. These are the three different assignments that you've had. This will help you prep for your test. So first question here: which of the following is false? Well, we know that E is equal to h nu. That's correct. Wavelength is not equal to frequency. The frequency would be equal to c divided by lambda. E is equal to h nu, which is, if you take that c over lambda and put it in for nu there, that looks good. And then here is the rearranged version of this, so that's good. So the wrong answer, the false answer is B there. Going on to question 2, you're asked basically to convert a frequency, right? This is 76 reciprocal seconds here as a frequency, and you're being asked to get a wavelength. So we're going to use that equation right there, at D in the previous problem, that the wavelength is going to be equal to c divided by nu. I kind of wrote my wavelength thing backwards there. C is basically 3 times 10 to the 8th meters per second, or seconds to the minus 1. And then the frequency, we're told, is 76 seconds to the minus 1. So seconds to the minus 1 will cancel out. We'll have units of meters. So we're going to be looking at 3 times 10 to the 8th, 3 exp 8, divided by 76. That comes to 3,947,368, which is 3.9 times 10 to the 6 meters if we round it to 2 places. So answer D is our correct answer there. Next question, again, it's a frequency going to a wavelength, same kind of problem. I'll write wavelength correctly this time. Wavelength is c over lambda, c over nu, excuse me. Lambda is c over nu. 3 times 10 to the 8th meters per second, s minus 1 means per second, divided now by 6.00 times 10 to the 10 hertz, which is the same thing as seconds to the minus 1, right? So seconds to the minus 1 again cancels out. 3 divided by 6 would be a half. 10 to the 8th divided by 10 to the 10th is going to be 10 to the negative 2. So a half times 10 to the negative 2 is going to be something like 5 times 10 to the negative 3, which we can do that one even without using a calculator. Alright, now we have a wavelength going to frequency, and the wavelength is in nanometers. I'm going to show you a trick here about dealing with that. So frequency, what's nu? C over lambda is nu, just rearranging the previous equation. We put the speed of light in, 3 times 10 to the 8th meters, seconds to the minus 1 meters per second. Now we've got 650 nanometers. Now 650 nanometers, we'd have to do a conversion. We can do that really easily. What we're going to do is just simply say 3 times 10 to the 8th meters seconds minus 1 over, nano means 10 to the negative 9th, so we'll just say 650 times 10 to the negative 9th meters. So that right there is equivalent to nanometers. We don't have to worry about the fact that that 650 is not between 1 and 10 like we usually do for our scientific notation. 10 to the negative 8 divided by 10 to the 8th divided by 10 to the negative 9th is going to be the same thing as 10 to the 8th minus negative 9, or 10 to the 8 plus 9. That's 10 to the 17th, so it's going to be a big number. 3 divided by 650 is going to be something around 10 to the minus 2, so something around 10 to the negative 15th seems reasonable. So I'm looking at answer A there and thinking it looks like a reasonable answer. 3 times 10 to the 8th divided by 650 times 10 to the negative 9th. And I get 4.6 times 10 to the 14th, so I think that's actually D is a better answer than A. It's easy to get confused about whether that power is positive or negative, so watch out for that. Seconds to the minus 1, of course, is the same thing as hertz, So that's our answer there. Answer D is our answer. All right, 5, same kind of problem. So nu is c over lambda, 3 times 10 to the 8th meters per second. And now we'll say 532 times 10 to the negative 9th meters, just like we did before. Meters cancels out. So 3 exp 8 divided by 532 exp 9 negative, and we get 5.6 times 10 to the 14th hertz, or seconds to the minus 1, which is going to be answer B. Now, looking at 6, we're doing the energy for this, and we're using gigahertz, and knowing that gigahertz is 10 to the 9th or a billion hertz. So we're asked to calculate the energy of that. Gigahertz is, of course, this is a frequency value, so we're going to use the equation E equals h nu, where h is 6.626 times 10 to the negative 34th joule seconds. That's a constant, Planck's constant. And then we're going to write the frequency in now as 2.4 times 10 to the 9th seconds to the minus 1, which is a hertz, right? Where I've used the giga to be my 10 to the negative 9th, and the seconds to the minus 1 is the hertz. So some translation of the units there. So 6.626 exp 34 negative, that's a pretty small number, times 2.4 exp 9. So 10 to the negative 34 times 10 to the 9th is going to be somewhere around 10 to the 25th. So maybe something in that ballpark. 1.6 times 10 to the 24th is 10 to the negative 24th is what I get. And again, this is the energy of a single photon, so it is pretty small. Similar problem now, except we have wavelengths, so we're going to use E equals hc over lambda because we're given lambda right here. So that's going to be 6.626 times 10 to the negative 34th joules seconds times 3 times 10 to the 8th meters seconds to the minus 1 divided by 632.8 times 10 to the negative 9th meters. That's where nanometers. Meters cancels out here. Seconds and seconds to the minus 1 cancel out there. We wind up with joules. Let's see what we get. 6.626 exp 34 negative times 3 exp 8 divided by 632.8 exp 9 negative. That's 3.14 times 10 to the negative 19th joules. So that's going to be basically answer A there for number 7. Let me say, just stop for a minute here and talk about this. If you're entering numbers that look like the ones in this problem on your calculator, there's better and worse ways to do that. And one way that you could get this problem wrong, and you absolutely should be trying to redo these problems in your calculator right now, make sure you're coming out with the same answer that I do. One way that can make this problem go wrong for you is what's called a hierarchy error, where your calculator gets confused about whether you're multiplying or dividing because of the order of operations. So the way I would recommend that you enter a number in scientific notation, if you're using, say, a Texas Instruments 80 plus calculator, I would enter the number as, so let's say I was doing 3 times 10 to the 8th, I would say 3, then I'd hit second and comma. Now, second and comma together, the second function of comma is labeled E or EE. That raises things to the power of 10. Then you're going to put in your well, this is actually positive, so you won't do a change sign. You're going to put in 8. So that would be 3 times 10 to the 8th. What that does is that treats that as one number. If you do 3 times 10 caret 8, 3 times 10 caret 8. That treats it as two numbers, and that'll lead to more hierarchy problems. So again, that's my recommendations on that, using that kind of calculator. And you'll kind of get the hang of it if you, again, are practicing these problems and making sure you're doing this. All right, so number 8, we're being given the energy, and we're asked to get the wavelength. So we're going to take the equation we used on 7, and we're going to solve it for wavelength. So E is equal to hc over lambda. What we're going to do is divide both sides by E and multiply both sides by lambda. E cancels out, lambda cancels out, so that gives us that lambda is equal to hc over E. So we plug those numbers in. 6.626 times 10 to the negative 34th is Planck's constant, joules, times seconds, not joules. The seconds to the minus 1. That's H. C is 3 times 10 to the 8th meters, seconds minus 1, and seconds cancels out at that point. And then we're dividing by E, which is 1.06 times 10 to the negative 13th joules. So joules cancels out. And if you notice, that is the energies we've been calculating these past two photons that we've calculated have been like 10 to the negative 24, 10 to the negative 19th. 10 to the negative 13th is quite a bit more. That's like 1,000,000 times more than 10 to the negative 19th. So that wavelength is going to be one that's typical of a high energy photon. And remember that wavelengths, as wavelengths go up, energy goes down. So this is going to be a shorter wavelength. Let's see what we get. So 6.626 second, comma, change sign negative 34. That's different from the subtraction sign on the calculator, of course. Then times 3 second, comma, 8 divided by 1.06 second, comma, negative 13. And that comes out to be 1.87 times 10 to the negative 12th meters is our wavelength for that. And that's A. And gamma radiation is a high energy, very short wavelength thing. So when we look at number 9 here, and we're looking at these parts of the spectrum, we're going from longest to shortest wavelength. So that's going to be lowest to highest frequency and lowest to highest energy, if we keep those things clear. And so gamma rays definitely going to be our highest energy here of all these. Ultraviolet's next. Visible's in the middle. Radio and microwave. So A is our best answer here. And again, on an open book test, that would be an easy question. If we do them here from highest to lowest energy, again, that's the opposite way of going. So we're going to have gamma rays are going to be over at the left. Gamma rays are more energetic than X-rays, so B is our answer here for that one. Okay, now looking at number 11 here, we've got statements about light, and we have to figure out which one is the true statement. So the wavelength of light is directly proportional to its frequency. That's not true. Wavelength is equal to c over lambda, so that's inversely proportional. So that's not true. The frequency of light is inversely proportional to its energy. E is equal to h nu, so that's directly proportional. So B is not correct. The energy of a photon of light is inversely proportional to its wavelength. We've used above E equals hc over lambda. That is inversely proportional because lambda is on the bottom. So that looks like our right answer. And the frequency of light is directly proportional to the speed of light in a vacuum. The reason that's wrong, if you look at the equation, it certainly looks that way, right? But the speed of light in a vacuum is a constant, doesn't change, so nothing, there's no change to look at there. So D is wrong for that reason. C is our correct answer there. Looking at number 12, we're talking about the Bohr model, and we're considering the energy necessary to excite an electron from 5 to 6 is either greater than, less than, equal to, or either equal to or greater than the energy necessary to excite an electron from 3 to 4. So there you can look at this kind of visually, or you can look at it quantitatively. What happens as the energy levels go up? You know, as N goes up, the spacing gets smaller. So the energy that would be necessary to go from 5 to 6 should be less than. You can also look at the quantitatively, you know, the 1 over n high squared minus 1 over n low squared is our term that is proportional to the energy change. So if you compared 1 over 9 minus 1 over 16, okay, versus 1 over 25 minus 1 over 36, and if you plug this in your calculator, you'd find that the 5 to 6 one is smaller. So either way you can rationalize that, it's got to be less than. That answer is C. So now if we're looking at emitting the lowest energy photon, first of all we have to make sure we're doing emissions. 1 to 2 would be an absorption. So now we have the case of 2 to 1, 3 to 2, or 5 to 4, and the lowest energy photon is going to be the 5 to 4 for the same reason we talked about in question 12. All of those are one level jumps. The Schrödinger equation basically does not calculate the precise position. It isn't used to compute the wavelength. It can be solved to find the probability of that. It doesn't necessarily prove that electrons have positive and negative spins, although that's part of the solution, but I think D is the best answer there for that. The Pauli exclusion principle states that no two electrons from a given atom can have the same 4 quantum numbers. They can have the same spin as long as they're in different orbitals. And 2 electrons can occupy an orbital if they have opposite spins. So either B or D is a good answer there. And the number 16 Hund's rule says that you have several orbitals of equal energy available in a given subshell. They enter singly with parallel spins. That's a good statement of that. No 2 electrons will share the same orbital isn't true. You can spin pair them. Hund's rule just discourages you from spin pairing them. It doesn't say anything about the charge, and the electrons having opposite spin this shared orbital, that's really more the Pauli principle than the Hund's rule. So A is our best answer there for that one. All right, so that concludes homework 3.1. We'll be back in a little bit with more of the homeworks.